Creating life seems like it should be pretty straightforward, like a slightly more complicated version of making a cake. The right ingredients, with room for a little variation. There's some chemical reactions in there. The right temperature on the oven. The right amount of time. And voila! You've baked up some moist, delicious life. Assuming you followed the recipe correctly, it should turn out, right? Well, maybe it's not quite that simple. What if you don't have a real recipe? Or what if you don't even know what a cake is? Scientists have been trying for decades to understand how a bunch of molecules turn into actual living organisms. So far, attempts to create life in a laboratory haven't panned out, which means we're probably missing some crucial ingredient or a necessary step. And if we're having trouble baking life cakes here on Earth, it makes it harder for us to know what cake looks like elsewhere. And that's a big speed bump in our search for extraterrestrials. I'm Laura Krantz, and this is Wild Thing, Space Invaders, a series about the search for extraterrestrial life, where we're looking, what we're looking for, and why we hope we're not alone. Let's go back to Oumuamua, that first interstellar object that caught our attention for a second. And let's say, for the sake of argument, that Harvard astronomer Avi Loeb, who we heard from in the last episode, is right. It is a light sail, a technological marvel that came from a distant civilization. Which means, of course, that someone is out there, somewhere in the universe. But what else can this tell us about them? Are they like us, or something completely different? How would we know what to look for? Well, one way to answer these questions is to try and get a better grasp of what life is here on Earth.
And so that's the best place to start.
That's Dave Brain.
And by life, I mean life on Earth as we understand it.
He's an associate professor of astrophysical and planetary sciences at the University of Colorado in Boulder. And he's really good at making these complex topics into something digestible, like a cake. And to go back to that analogy, we know there are some necessary ingredients for life here.
All life on Earth needs three things. It all needs an energy source. And so for us, that's ultimately sunlight. But it's not unreasonable to think that energy could come from elsewhere. And there are examples of life on Earth that gets its energy from chemical reactions deep in the ocean floor or chemical reactions underground. You could also conceive for other planets, maybe tides could be a source of energy. And so we generalize that to saying a source of energy.
So ingredient number one, energy.
The second one is some combination of 6 elements from the periodic table. So I remember it as CHNOPS. So it's CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur.
These 6 chemical elements are the most basic building blocks for everything else life needs, from RNA to DNA to amino acids, which leads us to our last ingredient.
The third one that life on Earth needs is water, and it has to be liquid water.
And why water?
We think liquid is a great medium to get these building blocks of life together.
Water is what we have on Earth, but scientists acknowledge that it might be different on other planets.
There might be some other liquid that's favorable for life. So for Saturn's moon Titan, we talk about liquid methane and liquid ethane as being great solvents and a good place to get these building blocks and materials together.
Water, or another liquid, plus those building blocks, plus energy. We're pretty positive these ingredients are the ones that got life started in Earth's primordial kitchen. Back in the 1950s, 2 biochemists named Stanley Miller and Harold Urey demonstrated this with a fascinating experiment. They took those 6 chemical elements, CHNOPS, which would have been present in early Earth's atmosphere. They suspended those chemicals over a pool of water representing Earth's early ocean, and then they zapped it with an electric current. a lightning bolt of sorts, a source of energy. After a week, that pool of water filled up with these more complex molecules that are essential to life. Now, these aren't living things in and of themselves. They don't do any of the things that life does, which we'll get into a little bit later. And making the jump from these complex molecules to actual life is still a black box. And again, we're only talking about Earth. But we do think this experiment shows that those three ingredients could be important to life everywhere, not just here, but throughout the universe.
Water is not rare. Water is incredibly common. Organic compounds are not rare. They're extremely common, not just on planetary bodies, but even just floating around in the universe. And so the ingredients are there, are widely distributed. There's no reason to think that that's not a universal phenomenon, that distribution and abundance of those molecules.
Frank Rosenzweig is a professor of biology at Georgia Institute of Technology in Atlanta, which is home to research centers exploring the origins of life, the detection of life, and chemical evolution. Frank heads up another one of those centers, a branch of NASA's Astrobiology Institute. Astrobiology, you say? Well, that sounds intriguing. I'll get into more detail on that in a minute, but specifically, Frank's research looks at how life becomes more complex. How do we get from single-celled organisms to multicellular ones? Which gets back to my earlier question. Is there a formula, a recipe for life? What Urey and Miller, those biochemists from the 1950s, discovered, that energy plus building blocks plus water gives us the more complex molecules essential to life, that does feel a little like a recipe, at least in part.
To me, that's fairly compelling evidence that at least that part of the equation, that formula exists. The physics and the chemistry behind it are pretty straightforward. That doesn't lead you to cellular life.
Our black box. We don't have our Frankenstein moment yet, where we combine raw materials and energy and then get to yell, "It's alive!" The bridge between complex molecules and cellular life is missing, so to speak.
But, the bridge between Urey Miller and a functioning cell, the chasm is a lot narrower, let's put it that way, than it was 75 years ago. And I'll just leave it at that. If I had the experiments that would get us the rest of the way, I would be busy executing them in anticipation of a Nobel Prize.
Okay, so we have an idea of what life needs, but we still don't know what it is. When we ask the question, what is life? We can only try to answer it based on what we know about what's living on this planet. Dave Brain again.
Searching for life on other worlds is a hard enough task. Searching for something that you don't know what it is makes it colossally harder. Searching for your keys under the lamppost, that may not be where the keys are, but that's the place where there's light. So I think a great place to start is by searching for the kind of life that we think developed on Earth, and then understanding to the best of our ability what that life requires.
Okay, forget the kitchen for a minute. The Earth is a street lamp now, and in its light, we're surrounded by life. Plants, animals, insects, bacteria, fungi, slime molds, algae, all kinds of shapes, sizes, colors, abilities. Plenty of life forms to study and observe, to figure out how they work and how they emerged. And even if we still don't know how to create life from scratch, we can easily identify and define what life is.
We don't have a working definition about that.
We don't?
We're searching for life and biosignature detection. But something we haven't reconciled yet is, what is life?
Well, that's gonna make things a little more complicated. Meet planetary scientist Natalie Cabrol.
Of course, if you have a flying saucer or rabbit jumping in front of you, I guess that's pretty obvious. But it may be that life is something different than what we have now. And then you can be searching for a long time for something you don't know what it is about. So then you are bumping into the question of, am I going to be able to recognize it, even if I have it in front of me?
She's an energetic French woman with close-cropped silver hair and several bracelets that bang against the table as she makes her point. We met at the SETI Institute in Mountain View, California. SETI, which is an acronym you may have heard, stands for the Search for Extraterrestrial Intelligence. Something I didn't know is that SETI is an entire field of study, like genetics or biology. There are SETI centers and organizations all over the world. The SETI Institute in California is among one of the most well-known, and Natalie Cabrol works there as the director of the Carl Sagan Center for the Study of Life in the Universe.
What we do look for the origin, nature of life, and we search for it from microbe to ET.
We think we know what life needs. We just learned about that.
We are trying to understand what life does so that we can start to chart that.
As Natalie just said, we know life does certain things. In fact, what life does is how the dictionary defines life. Life reproduces. It has a metabolism. It uses energy and consumes nutrients. It evolves. But even those categories are kind of loose, and they still don't tell us what life is. Scientists have started thinking about all kinds of hypotheses, ones that are pretty far away from the realms of traditional biology and biochemistry.
And this is coming from quantum physics. This is coming from neuroscience, from artificial intelligence. Things that are not necessarily, obvious connection to the traditional astrobiology realm.
Because this question of what is life doesn't just belong to scientists. Defining life has been the purview of poets, philosophers, doctors, high priests, high-energy physicists, and everyone in between. I'll get back to some of her thoughts in a little bit, but it's clear that what seems like a simple question, what is life, is actually very hard to answer. A whole field of study has cropped up around it. Astrobiology. I thought the name sounded like a group of high-tech biologists who use some modern engineering to send little probes up to planets and moons and asteroids, take samples, bring them back, and look for evidence of life, dead or, alive. Turns out, like my cake analogy, this idea is only half-baked. First off, astrobiology is not just about biology.
It's so inclusive of fundamental physics, organic chemistry, geochemistry, evolutionary biology.
That's Micah Scheibel. He's a researcher at Georgia Tech and also collaborates with NASA as part of their astrobiology and space exploration programs. He's more on the chemistry side of things, which is just fine by him.
Our lab tries to stay away from the sticky stuff, the biology. The goo scares me. I prefer metals and rocks. Things that they're not sticky, they don't bite.
Also, despite a name that implies outer space, a lot of astrobiology is figuring out the mysteries of our own origins, where we might have come from in space. Although astrobiologists definitely get to send some stuff out to the cosmos.
We have to send missions to Titan, the moon around Saturn, where the Dragonfly mission is going to look at methane lakes.
Titan also has liquid water and a lot of those chemical building blocks, which makes it an ideal place to look for signs of life. Micah's specialty, though, is something called ionizing radiation, which is a type of radiation, of energy, that can disrupt atoms and molecules.
Looking how radiation can sort of change the molecular structure of the molecules that are available for the beginning of life. Kind of like, all of our superheroes are spawned from radiation. We think that the beginnings of life, the beginnings of the molecular basis for life began in the cloud of gas and dust that condensed around the newborn star.
Most of the materials in that cloud are pretty simple, like the minerals you find in sand, and molecules of methane, ammonia, and carbon monoxide, and water. But this new star they're all clustered around is putting out a ton of radiation.
That can then produce new molecules by breaking the molecular bonds. So the radiation comes in. It's got enough energy to break the bond between a carbon and an oxygen. So now you have two radicals that are floating around, and if they find something else, they can react with it and form more larger and more complex molecules.
In other words, this radiation could be what turns these simple building blocks into the more complex chemicals that are central to life, the same way that electricity did in the Urey Miller experiment we heard about earlier. Because they are so exposed to radiation, this transition from simple to complex chemicals has happened on asteroids since, well, forever. And when asteroids slammed into Earth billions of years ago, they delivered those complex chemicals and also water, potentially seeding the Earth with these necessary elements for life.
So what we're interested in is when that radiation hit a surface of an asteroid, what happens? What new chemicals form? How does that depend on the composition of that surface? And then how does that material play a role in the potential beginning material that was available for life?
Setting up a laboratory on an asteroid isn't actually possible. So Micah has to use satellites and experiments here on Earth to get a lot of the information he needs. He couldn't do his work without some pretty technically savvy people. It illustrates the point that astrobiology needs a wide range of skills and out-of-the-box thinking.
We have people who are engineers, people who are orbital mechanics guys who can control the spacecraft missions. And so for me, astrobiology is all of that. It's the science and the technology working together to understand more about the place we came from, that is, our solar system, our galaxy, our universe.
Think of this search for the origin of life as a million-piece puzzle. The chemists, like Micah, are in one corner working on their stuff. The physicists are in another, the biologists are over here, and the geologists have their own chunk. Every once in a while, a chemist will look up and say to a physicist or a biologist, "Hey, I think I've got a piece that might fit with one of your pieces." And they'll try to connect different parts together to make a bigger picture.
We want to know how life goes from the beginnings to, where we're at right now, what life is. How do you draw that line from the newborn star to this podcast?
I mean, this podcast really is the pinnacle of human intelligence. But, you might be wondering, where are the aliens in all of this? Truth is, most of these scientists aren't thinking about intelligent life, at least in their day-to-day. They're starting pretty small.
I think there's more likelihood of very simple single-cell biologic life being more abundant.
Yeah, I think there's other life in the universe for sure. I think developing into intelligent life is a much harder question that requires not just the right environment, but a whole bunch of other factors come into play.
I still think it's possible that there's life on Mars, microbial life under the surface.
I think if there is life in our solar system that we could actually go find in our lifetimes, which would be quite exciting. I think it's going to be microbial life. I think it's probably going to be single-celled.
A gleam comes into Jennifer Glass's eyes when she talks about this possibility. Jennifer is another scientist I spoke with at Georgia Tech, and if you're wondering why I'm talking to all these Georgia Tech people, it's because they have one of the leading astrobiology programs in the world. Jennifer is over in the geology corner of this astrobiology puzzle, a professor of Earth and atmospheric sciences.
I'm interested in different kind of alternative substrates that life could inhabit on other planets or other moons in our solar system.
A substrate is the type of surface that an organism lives on.
I'm also interested now in the possibility for life in our solar system on colder planetary bodies, and I still think there's a chance that there is deep subsurface life on Mars.
She's really pumped about the possibility of life on Mars, not least because that's something we might actually find in our lifetime. She's gone to some strange places looking for microbes, places you wouldn't expect anything to be living, let alone thriving.
We were just walking around in these salt ponds just south of San Diego that are right at the limit of life, right where we know the lowest possible amount of water in these brines for life to survive.
In fact, she says, scientists have found microbes in all kinds of places on this planet, in some pretty unforgiving environments.
I think they've found them in nuclear reactors. We can deep freeze cells and then revive spores of them. Goodness, there's so many weird places.
Nuclear radiation, extreme cold, extreme salinity, the heat of the ocean's thermal vents, acid lakes, deep in rocks.
If they're under such harsh conditions down there on Earth, why not on Mars? Probably not on the very surface because it's just too harsh of conditions, but, a few meters down.
Microbes are abundant. Scientists guess that the number of species is around 1 trillion. The estimated number of individual microbes on Earth is thought to exceed the estimated number of stars in the universe. And they are everywhere, in places where we never even thought to look because they seemed too, extreme, at least for us.
Kind of blows my mind because I guess I give these microorganisms a lot of credit. They can just basically do things that we can't, and so it really makes me wonder, is that really the limit, or are we going to be able to find something even lower? Because they always surprise us, basically.
And those surprises are what have Jennifer so excited about what we might discover.
Potentially, we could know if we could be studying those fossils, potentially, of ancient life, or, maybe even finding modern life.
What's super cool is that this is a new field. We really only figured out how tough microbes are a little over 60 years ago. A scientist went looking for life in Yellowstone National Park and realized there were bacteria thriving in 175-degree water. Life is clearly comfortable in places that we humans will never be. And that opens up a lot of possibilities. Natalie Cabrol again, the director of the Carl Sagan Center.
Basically, we still have to find a place on Earth where life is not. And that changed everything, because all of a sudden you realize that you might be on a planet or a moon or whatever body of the solar system, for that matter, outside of what we call the habitable zone, and still have what now we call habitable environment.
Basically, we have a lot more places to look for life.
The perfect example of that are Mars and the icy moons. So Mars has no atmospheric shelter, right?
Oh yeah, shelter is the other thing, the fourth thing that we think life needs. Something that provides protection from cosmic radiation and asteroids, like an atmosphere or an ocean or being deep in some rocks. Mars doesn't have much of an atmosphere, so the theory had been that it couldn't support life. It was too exposed.
But from the geology we see and from the record that we have now from all of these missions, we can see that first it was not always the case. So there is a chance that life started. And we know that, the hardest thing for life to do is to stop, which means that we probably can say safely that life is a pest. And when it's somewhere, it's really, really hard to get rid of. So it's probably somewhere in there, if it started, and just has tons of places on Mars where it could still be in the subsurface.
Of course, the thought is that even with shelter, anything living on Mars will still need those three other elements we learned about with Dave Brain back at the beginning of this episode.
It all needs an energy source. CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Water, and it has to be liquid water.
So if these three things are what life that we would recognize needs, and life is abundant on Earth, living in all kinds of harsh and inhospitable environments, doesn't it make sense to think that these ingredients, and therefore life, would be abundant on other planets?
So I think that's how people are thinking right now when they're looking, when they're trying to understand what makes another world habitable, what other life might be like. But I think everyone acknowledges that it could be completely different than what we experience here on Earth. But then how do you look for that? Where do you even start? I don't know.
Oh man, this puts us right back where we started. What is life? How does it get started? And then what does it take for it to become intelligent, create a civilization, build a spaceship, visit other galaxies? We can't even try to answer those yet. Not until we figure out the basics. All of my conversations at Georgia Tech really reinforced this idea that astrobiology is, in many ways, rooted in the search for the origins and nature of life on this planet. As people told me over and over again, since we only have Earth as our example, that's our baseline for understanding how life might form elsewhere.
We have to sort of ponder deeply life here and life's origin on this planet, its early evolution, its elaboration into all the forms that we have in front of us now, and not just how all that happened, but what are the signatures of life as we know it. And so, yeah, it is very Earth-centered, and I think that people have joked about astrobiology, saying that it is the one scientific discipline whose object has never been found. But in fact, that's not true.
It's important to remember that we've already found it, right here, in places we never thought to look before. So while it may feel like we're going around and around and trying to understand life, we're learning so much, which gives us a better idea of where to look going forward. If we want to talk about extraterrestrials, we need to break that down into the necessary components, the smallest pieces, and then build up from there. If we can nail down the basics, then we can start making predictions about how life elsewhere might evolve and what we should be looking for. Aliens, we're coming for you. Slowly. And now, I want to blow your mind. Earlier in this episode, I told you I'd come back to some of Natalie Cabrol's ideas about how we think about life.
We are trying to define it by the fact that, it metabolizes, it reproduces, and it does a number of things. But there are a number of those characteristics that you can translate into what we consider being non-living.
Fire metabolizes. It uses energy. But most scientists don't consider it to be alive. Neither are viruses, even though they reproduce.
And so I think that it's an interesting scientific exercise to say there is the living and the non-living. But once we do that, we boxed ourselves in, thinking that maybe there is a difference.
And some people believe we should think outside that box, turning to quantum physics and neuroscience, information technology, and artificial intelligence to come at the idea of life from a different angle.
All of them seem to be converging towards thinking of life and consciousness, the two of them being associated in that, interestingly enough. Life as a force and not a thing.
Life as a force, not a thing. This sounds very Star Wars, but what does it actually mean?
Right now we are looking on the narrow end of the microscope or the telescope about life and say, it does this and it does that. And so to have life, you have the combination of this, and that.
The ingredients, so to speak. But if you are looking at this through the lens of quantum physics, life isn't something that happened because you had the right conditions on the right planet, or anywhere else in the universe for that matter.
It's something that is here at the beginning of the universe. They get down to the basics of saying, in the universe, everything is energy. And energy becomes information when there is something to look at it and translate that energy into information. That's the consciousness part. This is really cool.
All right, let me see if I get this. We all know there was a tremendous amount of energy released at the beginning of the universe, the Big Bang. All that energy is still out there, bouncing around. And life, these scientists argue, is that energy, being aware of itself.
What we call living is just the moment where we start to realize that something is alive. That doesn't mean it is not alive before that.
Which, in Natalie's opinion, seems like a game changer. It changes how we would search.
You don't have to search for something if the entire universe is alive. Whatever you see around you is a manifestation of a process that is called life. I'm going to push it. Even this table is a manifestation of that. You don't think you can have a metaphysical discussion with the table, probably will take you some time, but this thing is doing a number of things. It's sharing energy. It's sharing information at a pace that you cannot recognize, but still basically doing what you are doing. And so when you are looking at the night sky And looking at worlds out there, you're trying to understand the diversity of this manifestation. I think it's beautiful in itself. That doesn't mean that you won't have another extraterrestrial intelligence, because it might just be there, right?
Whoa. To be totally honest, I have a tough time wrapping my head around this. But I don't know that what Natalie is saying changes the reasons we're searching. If life is a force and permeates everything, and we are just the consciousness of the universe, don't we still want to find other examples of that consciousness elsewhere? Whether you think quantum physics will hold the answers, or you prefer to stick with everyday physics and chemistry and biology, based on what we've heard so far, I think it's likely that life is out there. In fact, I'd be willing to put money on it. But before I decide how much, I kind of want to know what the odds are of actually finding something. Turns out, there's an equation for that. Well, it's really more of a thought experiment created by a man named Frank Drake.
What is it we need to know about to understand how many civilizations there might be in space? So I thought that through, and I realized, well, you need to know how many Earths there are, and how often life appears, and how often life evolves intelligence.
On the next episode, we'll hear how Frank Drake came up with his famous equation. And now, 60 years later, what odds he gives us on finding something. And we'll take a walk through the solar system as we try to understand one of the biggest obstacles to meeting alien races, the sheer vastness of space.
We are so influenced by popular media and science fiction, and all of a sudden we are in the Millennium Falcon traveling at the speed of light, so we can go from one planet in a star system to another planet in another star system, and it seems that it's just been a few seconds, and those things are clearly way out of reach.
That's coming up on Wild Thing, Space Invaders. Want to learn more about the ins and outs of astrobiology? Check out the Astrobiology Primer, which has research from scientists all over the world. I've linked to their website on social media, at Wild Thing Pod on Facebook, Twitter, and Instagram. And check out our website, wildthingpodcast.com. That's Wild Thing Podcast, all one word. If you're enjoying Wild Thing, please subscribe and leave us a review on Apple Podcasts, Spotify, Stitcher, or wherever you listen to good stories. Also, definitely tell your friends, because all of this really helps get the word out about the show and makes another season possible. This podcast is a production of Foxtopus Inc. Our executive producer is Scott Carney, editing is by Alicia Lipinski, and the score and sound mixing come from Louis Weeks. I'm your host and creator, Laura Krantz.